Okay, so this will just give a background on wave.
In today's video, we're going to look at the basics of waves, including how to label the different parts, how to calculate the wave speed, and the differences between transverse and longitudinal waves. The first thing to understand about waves is that they transfer energy from one place to another, but they don't transfer any matter. So when light waves pass from a phone screen to your eye, or sound waves pass from the speakers to your ear, only energy is being transferred. Sometimes, though, we can interpret that energy as meaningful information, which is why our brain is able to build up images and tunes from the light and sound that it receives. To travel from one place to another, the waves vibrate or oscillate, as we can see in this displacement distance graph. The distance is how far the wave has traveled from the starting point, while the displacement is how far from the equilibrium point the wave has oscillated, so how far it's gone up or down. The maximum displacement is known as the amplitude, while the distance of one entire oscillation is called the wavelength. So that could be from equilibrium, up, down, and back up. Or it could be from the very top of a wave, which we call the crest, down and back up to the next crest. It just has to be one entire oscillation. And the opposite of the crest is called the trough. Now, sometimes you might see a displacement time graph instead, which looks pretty much the same, but because we have time on the x-axis instead of distance, the length of one complete oscillation would be the time period instead of the wavelength. And the time period is just the time it takes for one complete oscillation. The benefit of knowing the time period is that we can then use this equation here to work out frequency, which is measured in hertz, and is the number of complete oscillations per second. To see how it works, imagine that each oscillation takes 0.5 seconds. Or in other words, the time period is 0.5 seconds. This means that there must be a total of 2 oscillations per second. So the frequency is 2, which is what we'd get if we did 1 divided by the time period of 0.5. We can also use the equation the other way around. So time period equals 1 over frequency. So if we were told that the frequency of a wave was 4 hertz, which means 4 oscillations per second, then to find the time period, we'd just do 1 divided by 4, which tells us that each oscillation must be 0.25 seconds. The next equation to know is that we can find the speed of the wave, so the wave speed, by multiplying the wavelength by the frequency. So basically, we multiply how long each wavelength is by how many there are per second. And that will give us the total distance they travel per second. To see how this works, let's imagine we had a sound wave that had a frequency of 400 hertz and a wavelength of 70 centimeters. What is its wave speed? Well, in this case, all we'd have to do is convert the 70 centimeters to 0.7 meters, because we always want our wavelength in meters, and then multiply it by the frequency of 400 hertz, which gives us 280 meters per second as our wave speed. The last thing we need to look at are the differences between transverse and longitudinal waves. In transverse waves, the oscillations are perpendicular to the direction of energy transfer. or the direction in which the wave is moving. Which is why on our drawing, the vibrations are going up and down, whilst the overall wave is traveling from left to right. Most waves we can think of are transverse, including all electromagnetic waves, like light and radio waves, ripples and waves in water, and the waves of strings like on a guitar. Longitudinal waves, on the other hand, have oscillations that are parallel to the direction of energy transfer.
I hope you're getting the differences.
Yes.
Okay.
This one's a bit trickier to get your head around, but basically it leads to some regions that are more spread out and other regions that are more compressed, because the wave's vibrating back and forth. In motion, it would look as if this area of compression is moving from the left to the right within the wave. Examples of longitudinal waves include sound waves and some types of shock waves, like seismic P waves. Anyway, that's it.
Okay. Okay, so that's awesome. Now I'll be sharing another one immediately. Okay, should be coming up in just a minute. Come on. Okay.
We're all familiar with waves, especially water waves. But sound and light are just as wavy, and they're even more common. Luckily, we can learn a lot about sound and light waves by looking at water waves. Here are some continuous circular waves being made by a point source, as shown from above, so that we can see their crests moving outwards. We can also show the waves side on, where it's easier to see what's making them. For example, here a rod is being dipped in and out of the water. How would you describe a wave to a friend? We can describe the waves using their wavelength, which is the distance between their crests. It's also the distance between their troughs, because this is the same distance. We'll call the wavelength lambda, which is a letter that stands for L in the Greek alphabet. Now we'll fade out the overhead view and just look at the side view to make the waves look simpler. And here's a boat to show some of the strange properties of waves. How is the boat moving differently to the wave? Notice how the wave is moving left to right, but the boat only moves up and down. You can check this out next time you're in a boat. The speed of a wave is how fast it's traveling from left to right here, and is usually given the symbol V, which stands for velocity. Velocity is another word for speed. Notice how the speed of the wave is constant, and each crest moves at the same speed as the others. But the boat's up and down speed changes, and you can see that it's moving fastest in the middle of its cycle. This cyclic type of movement is called simple harmonic motion, and we'll cover that later. A pendulum is another example of simple harmonic motion, although it moves horizontally instead of vertically. The amplitude of a wave with symbol A is how high it moves up and down compared to a flat, calm surface. High amplitudes are caused by the source having more energy and dipping further into and out of the water. The guy on the boat would would notice that he would rise and fall more, so he'd get a more energetic ride. The wave's frequency, given the symbol F, is the number of waves being made each second. The frequency is also the number of waves passing by the guy in the boat each second. Here, only one wave is passing per second, so scientists say that its frequency is 1 Hertz. Hertz is the unit of frequency, and it just means waves per second. It's usually shortened to Hz. This unit was named after the famous German scientist Heinrich Hertz, who proved the existence of electromagnetic waves, which we'll explain in another video. Interestingly, Hertz was not only a clever scientist, he could also speak Arabic and Sanskrit. Both of these languages are steeped in scientific and mathematical history. Does anything increase the frequency by dipping the source in and out more often? Let's double it from 1 to 2 Hertz. Looking at the wavelength, we can see that it gets shorter. We doubled the frequency and the wavelength looks about half what it was before. This means that when frequency increases, wavelength decreases, and vice versa. So we can say that frequency and wavelength are inversely related. That makes sense. When we increase the frequency, more waves are squeezed in, reducing the distance between them.
Okay. Now this explains. Well, I'm just doing. I just have to do this concerning the first. That's on waves. The first thing we talked about on wave. Today we'll actually be doing something on wave motion, but before then, I'm just trying to see, okay, just pay back for the lost time. You know, the last time we met, we were all working on equations, solving equations. So I did not have the time to really package most of these things. All right. One of the lessons we're looking at is still based on what we've done before. Before we go into our wave equation, it's still this. Okay. Let me see. Sorry, are you still seeing my screen?
Yes.
Okay, it's blank, right?
Yes.
Okay, let's see this then.
In this video, we're going to talk about waves and characteristic of waves, like frequency, wavelength, energy, amplitudes, minus the bottom number. Let's use that other equation.
Okay,
To compare the answer at a wave point period to the in this material.
No worry, let's do this one for now. That was not what I wanted. All right. Now, so today, let's go into types of waves. We've just looked at that. We have waves can be classified into 2 types. We have the transverse wave and the longitudinal wave. The transverse wave and the longitudinal wave. Now, from the video we just watched, we understood that if the direction of the propagation of the particles is perpendicular to the direction of vibration, when they are perpendicular, that means having angle 90 perpendicular, that means we say the wave is transverse. Now, examples of this transverse wave, remember we said if the direction of propagation is perpendicular to the direction of vibration of the medium, that wave is transverse. And examples of transverse wave, we have them as water waves, waves produced by a string, But if we consider most material medium, waves most times can be classified under mechanical waves and electromagnetic waves. If we consider material medium, waves can be classified into mechanical waves and electromagnetic wave. So what are mechanical waves? Mechanical waves are waves that require a material medium for their propagation. Please write that. Mechanical waves are waves that require a material medium for their propagation. An example of such kind of waves are the water waves and the waves in a string. Water waves and waves in a string. Okay. Have you gotten that, please?
Yes.
Okay. Now, electromagnetic waves. These are waves that do not require material medium for propagation. These are waves that do not require material medium for their propagation. Now, examples of these waves are the radio waves. Examples of these waves, we have them as the radio waves, the light wave, and even the X-ray. Okay. Now, while I said that transverse waves are waves that the direction of propagation is perpendicular to the direction of vibration, what is a longitudinal wave? Longitudinal waves, these are waves in which the direction of propagation is parallel to the direction of vibration. So that means transverse waves, they are perpendicular. Longitudinal wave, the direction of propagation is what? Parallel. Now, if the direction of the travel of the wave is the same as the direction of vibration in the medium, we know that wave is a longitudinal wave. Now, an example of such kind of wave is the sound wave. The sound wave is an example of longitudinal waves. Now, most times in longitudinal waves, the vibrating particles behave like spiral spring. They behave like spiral spring that has compressed regions and spaced out regions traveling around them. Now, the series of most of these compressed regions, most times, they are called compression. Let me see if I could get, okay. If I could just share this with you. Okay. Okay, can you see this? Can you see my screen?
Yes.
Okay. Now, this is an example of what I'm trying to say, that if the direction of vibration is perpendicular to the direction of travel, that means it's a transverse wave. Now, if it is parallel in the same direction, that is a longitudinal wave. Now, I was talking about that this is an example of longitudinal wave. Now, this series of spring together, these ones are called, you see these lines that join themselves together, they are called compression. But the ones that are spaced out are called refraction. The ones that are spaced out, let me see if I can write them out. Okay. I said they're called compression, while the other ones are called come in. What's this? Okay. Refraction. Okay. So with this now, this brings us to the equation of traveling waves. The equation of traveling waves. So I would be using showing you some videos that has to illustrate. Then I come together to wrap up something on equation of traveling wave, because we'll be using the equation of waves to solve some question. We're going to see some of these equations of waves, how did we come about it, and how to use them in a given situation. So let's look at this video on how we came about the equation of waves. Okay.
I want to show you the equation of a wave and explain to you how to use it. But before I do that, I should explain, what do we even mean to have a wave equation? What does it mean that a wave can have an equation? And here's what it means. So imagine you've got a water wave and it looks like this. And we graph the vertical height of the water wave as a function of the position. So for instance, say you go walk out on the pier and you go look at a water wave heading towards the shore. So the wave might move like this. You'll see this wave moving towards the shore. Now, realistic water waves on an ocean don't really look like this, but this is the mathematically simplest wave you could describe. So we're going to start with this simple one as a starting point. So let's say this is your wave. You go walk out on the pier and you go stand at this point, and the point right in front of you, you see that the water height is high, and then 1 meter to the right of you, the water level is 0, and then 2 meters to the right of you, the water.
Can you see my video?
Yes.
Okay.
Height, the water level is -3. What does that mean? It means that if it was a nice day out, right, there was no waves whatsoever, there'd just be a flat ocean or lake or wherever you're standing. But if there's waves, that water level can be higher than that position or lower than that water level position. We'll just call this water level position 0, where the water would normally be if there were no waves. So you graph this thing and you get this graph like this, which is really just a snapshot. Because this is vertical height versus horizontal position, it's really just a picture. So in other words, I could just fill this in with water and I'd be like, oh yeah, that's what the wave looks like. And if I were to show what the wave does, it travels toward the shore like this, and you'd see it move. So that's what this graph really is. If you've got a height versus position, you've really got a picture or a snapshot of what the wave looks like at all horizontal positions at one particular moment in time. And so what should our equation be? It should be an equation for the vertical height of the wave that's at least a function of the position. So this is function of, this isn't multiplied by, but this y should at least be a function of the position, so that I get a function where I can plug in any position I want. Let's say x equals 0, and it should tell me, oh yeah, that's at 3. So this wave equation should spit out 3 when I plug in x equals 0. When I plug in x equals 1, it should spit out, oh, that's at 0 height. So it should give me a y value of 0. And if I were to plug in an x value of 6 meters, it should tell me, oh, yep, that y value is -3. So no matter what x I plug in here, say 7, it should tell me what the value of the height of the wave is at that horizontal position. So what would this equation look like? Well, let's just try to figure it out. Y should equal, as a function of x,
it should be no greater than 3 or -3, and this is called the amplitude. So if we call this here the amplitude A, it's going to be no bigger than that amplitude. So in this case, the amplitude would be 3, but I'm just going to write amplitude. So this is a general equation that you could apply to any wave. And then look at the shape of this. This is like a sine or a cosine graph. Which one is this? Well, because...
Okay, is sine or cosine graph?
Sine.
Sine graph, awesome. So that's where we put the sine there.
At x equals 0, it starts at a maximum. I'm going to say this is most like a cosine graph because cosine of 0 starts at a maximum value. So I'm going to say that this is like cosine of some stuff in here. Now, you might be tempted to just write x, but that's not going to work. If I just wrote x in here, this wouldn't be general enough to describe any wave, because think about it. If I've just got x, cosine of x will reset every time x gets to 2 pi. So every time the total inside here gets to 2 pi, cosine resets. But look at this cosine. It resets after 4 meters. And some other wave might reset after 8 meters. And some other wave might reset after a different distance. I need a way to specify in here how far you have to travel in the x direction for the wave to reset. So x alone isn't going to do it, because if you've just got x, it always resets after 2 pi. So what do? I play the same game that we played for simple harmonic oscillators, and I say that this is 2 pi, and I divide by not the period
Lambda.
this time. This is not a function of time, at least not yet. It's not a function of time. This is just of x. So this wouldn't be the period. This would not be the time it takes for this function to reset. It would actually be the distance that it takes for this function to reset. In other words, what we call the wavelength.
The wavelength.
So the distance between 2 peaks is called the wavelength, and we represent it with this Greek letter lambda. So the distance it
Can you still see?
Yes.
Okay.
takes a wave to reset in space is the wavelength. That's what we would divide by, because that has units of meters. And then finally, we would multiply by x in here. That way, if I started x equals 0, cosine starts at a maximum, I would get 3. If I say that my x has gone all the way to 1 wavelength, and in this case, it's 4 meters. If I go all the way to 4 meters or 1 wavelength, once I plug in wavelength for x, that wavelength would cancel this wavelength. We'd get 2 pi, and this cosine would reset, because once the total inside becomes 2 pi, the cosine will reset. And that's what happens for this wave. It should reset after every wavelength. You go another wavelength, it resets. Another wavelength, it resets. And that's what would happen in here. So how would we apply this wave equation to this particular wave? Well, let's take this. It's already got cosine, so that's cool because I've got this here. You could use sine if your wave started at this point and went up from there, but ours starts at a maximum, so we'll use cosine. So we'll say that our amplitude, not just A, our amplitude happens to be 3 meters because our water gets as high as 3 meters above the equilibrium level, and we'll leave cosine in here. The 2 pi stays, but the lambda does not. Our wavelength is not just lambda, that's just too general. We got to write what it is, and it's the distance from peak to peak, which is 4 meters, or you could measure it from trough to trough, or you could call these valleys valley to valley. That'd also be 4 meters. Regardless of how you measure it, the wavelength is 4 meters. And then what do I plug in for x? I don't, because I want a function. This is a function of x. I mean, I can plug in values of x. Let's do it. Let's see if this function works. If I leave it as just x, it's a function that tells me the height of the wave at any point in x, but we should be able to test it. Let's test if it actually works. So let's take x and let's just plug in 0. So if I plug in 0 for x, what does this function tell me? It tells me that the cosine of all of this would be 0. And I know cosine of 0 is just 1. So it tells me that this whole function is going to equal 3 meters. And that's true. The height of this wave at x equals 0. So at x equals 0, the height of the wave is 3 meters. So that one worked. Let's try another one. Let's say we plug in a horizontal position of 2 meters. If I plug in 2 meters over here, and then I plug in 2 meters over here, what do I get? This is going to be 3 meters times cosine of, well, 2 times 2 is 4, over 4 is 1, times pi, so it's going to be cosine of just pi. And the cosine of pi is -1. So I'm going to get -3 out of this. -3 meters, and that's true. The height of this wave at 2 meters is -3 meters. So this function's telling us the height of the wave at any horizontal position x, which is pretty cool.
However, you might have spotted a problem. You might be like, wait a minute, that's fine and all, but this is for one moment in time. This wave's moving. Remember, this whole wave moves toward the shore. So at a particular moment in time, yeah, this equation might give you what the wave shape is for all values of x. But if I wait just a moment, boop, now everything's messed up. Now at x equals 2, the height is not -3. And at x equals 0, the height is no longer 3 meters. It only goes up to here now. So what do? How do we describe a wave that's actually moving to the right in a single equation? Well, it's not as bad as you might think. Let me get rid of this. Let's clean this up. We're really just going to build off of this function over here. What I really need is a wave equation that's not only a function of x, but that's also a function of time. So this function up here has to not just be a function of x, it's got to also be a function of time, so that I can plug in any time and any position, and it would tell me what the value of the height of the wave is. So how do I get the time dependence in here? Well, I'm going to ask you to remember, if you add a phase constant in here, remember if you add a number inside the argument to cosine, it shifts the wave. In fact, if you add a little bit of a constant, it's going to take your wave and actually shifts it to the left. So we're not going to want to add. If we've got a wave going to the right, we're going to want to subtract a certain amount of shift in here. But subtracting a certain amount, so that's cool, because subtracting this certain amount shifts the wave to the right. But if I just had a constant shift in here, that wouldn't do it. Like the wave at the beach does not just move to the right and then boop, it just stops. It just keeps moving. We need a wave that keeps on shifting. So you might realize if you're clever, you could be like, wait, why don't I just make this phase shift depend on time? That way, as time keeps increasing, the wave's going to keep on shifting more and more. So if this wave shift term kept getting bigger as time got bigger, your wave would keep shifting to the right. You'd have an equation that describes a wave that's actually moving. So what would you put in here? It might seem daunting. You might be like, man, that's going to be complicated. How do we figure that out? But it's not too bad, because just like the wavelength is the distance it takes for the wave to reset, there's also something called the period. And we represent that with capital T. And the period is the time it takes for the wave to reset. So if I wait one whole period, this wave will have moved in such a way that it gets right back to where you couldn't really tell. It looks like the exact same wave, in other words. So we show that over here. Let's say you had your water wave up here. I take this wave. If you wait one whole period, the wave will have shifted right back and it'll look like it did just before. So that whole wave's moving toward the beach. So if you close your eyes and then open them one period later, the wave looks exactly the same. So we're going to use that fact up here. We need this function to reset, not just after a wavelength, we need it to reset after a period as well. So how do we represent that? We play the exact same game. We say that, all right, I can't just put time in here. What I'm going to do is I'm going to put 2 pi over the period, capital T, and then I multiply by the time. That way, just like every time x went through a wavelength, every time we walk one wavelength along the pier, we see the same height, because this becomes 2 pi. Every time we wait one whole period, this becomes 2 pi, and this whole thing is going to reset again. So this is the wave equation, and I guess we can make it a little more general. This cosine could have been sine, so if you end up with a wave that's better described with a sine, maybe it starts here and goes up, you might want to use sine. And the negative, remember the negative caused this wave to shift to the right. You could use negative or positive because it could shift right with the negative, or if you use the positive, adding a phase shift term shifts it left. So a positive term up here would describe a wave moving to the left. And technically speaking, you can make it just slightly more general by having one more constant phase shift term over here to the right. If we add this, then we could take into account cases that are weird where maybe the graph starts like here and neither starts as a sine or a cosine. You'd have to draw it shifted by just a little bit. But in our case right here, you don't have to worry about it because it started at a maximum, so you wouldn't have to have that phase shift. And this is it. This is the wave equation. This is what we wanted. A function of position and time that tells you the height of the wave at any position x, horizontal position x, and any time t. So let's try to apply this formula to this particular wave we've got right here. So I'm gonna get rid of this, right? This was just the expression for the wave at one moment in time. So maybe this picture that we took of the wave at the pier was at the moment, let's call it t equals 0 seconds. So at t equals 0 seconds, We took this picture, that's what the wave looks like, and this is the function that describes what the wave looks like at that moment in time. But we're going to do better now. Now we're going to describe what the wave looks like for any position x and any time t. So let's do this. What would the amplitude be? That's easy. It's still 3. The wave never gets any higher than 3, never gets any lower than -3, so our amplitude is still 3 meters. And since at x equals 0 and t equals 0, our graph starts at a maximum, we're still going to want to use cosine. So we come in here, 2 pi x over lambda. Well, the lambda is still lambda, so lambda here is still 4 meters, because it took 4 meters for this graph to reset. You had to walk 4 meters along the pier to see this graph reset. That's a little misleading. I mean, you'd have to run really fast. The wave's going to be moving as you're walking. So I should say, if you're standing at 0 and a friend of yours is standing at 4, you would both see the same height because the wave resets after 4 meters. Would we want positive or negative? Since this wave's moving to the right, we would want the negative. I wouldn't need a phase shift term because this starts as a perfect cosine. It doesn't start as some weird in-between function. The only question is, what do I plug in for the period? So I would need one more piece of information. If I'm told the period.
Okay, awesome. I'm going to stop here. And I'm going to give you the various forms of the wave equation, because we should understand all the forms of the wave equation. So whatever the questions come out from, we'll be able to answer this question. Okay, one of the first forms of the wave equation, one of the first forms of the wave equation, if you have a wave equation, coming with y is equals to sine theta or cos theta, definitely we understand that theta is, you remember angular velocity. When we talked about angular velocity was theta over t, right?
Yes.
Yeah, angular velocity was theta over t. Now, if we have, oh, sorry. Okay. Where is my, okay. Now, if we have a wave equation as this, then we understand that angular velocity in this case, which is theta over t, can be written as where is it? Okay, can be written as y is equals to wt, because theta already, remember that w is equals to theta over t. So if we cross multiply, we should be having it as theta is equals to w, which is wt. So with this now, we can proceed that generally a wave equation that has an amplitude and a constant angular velocity can be written as this. Okay, can actually be written, as this. Okay, now this W is the angular velocity, the T is the time, and then the phi there, which is the phase angle, that's a constant that the wave did not start from the origin. And please write there that that phi is equals to the angular distance. The phi there is the angular distance. We can also call that the phase constant. We can also call that the phase constant. Now, there's another thing we need to note, that the phase constant is, the phase constant, we can also represent it as this. Now, if we represent the phase constant is equals to 2 pi x over lambda, that means our next equation can be, that means our next equation if we represent phi as 2 pi x over lambda, and remember we called that phi, we called that a constant. So that means we can write our equation. We can write our equation as this. We can write our equation as this, that a sine plus or minus. Remember, when you use cosine, you saw minus or plus. But now that it is sine, it could be plus or minus. But remember, we said that a sine wt, that's the angular velocity times the time, plus or minus 2 pi x over lambda, that is our constant already. From here now, we can write, we can illustrate this. We can illustrate this as this. So this is our equation 2, that y is equals to a sine wt plus or minus kx. Okay. Now, from here, the next thing we need to do, we need to understand from here is that, remember, we did understand that W is equals to 2 pi t, 2 pi big T. I hope you remember, okay? I'm coming. We remember that W, that's the, sorry, not W, the angular velocity was actually 2 pi. Okay. The angular velocity was actually 2 pi over T over big T, which is also the same thing as 2 pi F. I hope. So if we substitute this into equation 2, this becomes a sine 2 pi, okay? This becomes a sine 2 pi t over big T plus or minus 2 pi x over lambda. Okay, so this can be equation 3. Okay. Now, if we factorize that equation, sorry. If we factorize that equation, we should be having something like this. By factorizing, I'm going to call this equation 3, and I'm going to call this equation 4. By factorizing, we should be having something like a sine, sorry, okay, we should be having something like a sine I'm coming. This is not giving me what I want. We should be having something like this is equation 4, not equation 5. All right, we should be having something like this: a sine 2 pi over lambda bracket lambda t small t over big T plus or minus x. That's actually what we should be having. Why is this not, oh God. Oh no, come on. just lost the ability to edit that now. Sorry, did you get all those things I wrote? I
Yes.
can't believe I just lost some of them. Okay, please. Let me post this again. This is equation 4. This should be equation 4. Okay. Okay. All right. Now this should be a sine 2 pi over lambda bracket lambda t over t plus or minus x. That's if by factorization. Okay. Now, but remember that v is also, that's the v, which we call the linear velocity or the linear speed, is also equal to frequency times lambda, and lambda is also equals to vt. So that means we can have an equation like this. We can have an equation like this. We can have an equation that's, recall that v is equals to f, that's frequency times lambda, and lambda is equals to vt. Therefore, equation 5 becomes 2 pi. Remember that lambda t is substituted for the vt plus or minus x. Lambda t over t, we know definitely that v is equals to, from this equation here, which we have lambda is equals to vt, v is equals to lambda over t, lambda over the t here, and that gives us v is equal, that's a is equals to a sine 2 pi over lambda bracket vt plus or minus x. Now with this, now we have, sorry, coming, let me cover this. Okay, with this now we have about these 6 equations. Or what am I doing? Oh God, wait. Okay, I now understand. This is covering this. This is covering this. Oh no. Please, this equation 4. Let me see if I can erase this one. Wow, everything just disappeared. All right, but please note that the equation 4 we are using is not the same. The equation 4 we are using here is not the first one, rather is this other one. So please, okay, I think I should be able to erase this. Good, that's awesome. Awesome, that's a very good one now. Okay, beautiful, beautiful. Okay, so this is it now. So we can use any of these equation, a sine brackets wt, that's, sorry, angular velocity plus or minus the phase angle. Remember the phase constant is 2 pi x over lambda. We can use equation 1, equation 2, depending on what we're given in a question. So if you have written all these things down, let's go straight to the application of all these formulas. How do we use them? You're going to be looking at different ways to use them. Remember, the positive sign is when the wave is propagating in the x direction. That's in the negative x direction. And the negative is for when it is propagating in the negative, in the positive x direction. All right, with this now, have you written those things down? Because I'm about changing it very soon.
Yes.
Okay, let's solve this question. A wave is given by the equation. Okay, I'm going to be posting the question then. Now, let's look at this. This question. A wave is given by the equation y is equals to 0.03 sine 2.2x minus 3.5t, where x and y are in meters and t is in seconds. Find the amplitude, the wavelength,
Yeah.
the period, and the speed of the wave. Okay. Please let me know if you've written the questions down. This now, I'd like to ask you, let's come back to all the equations we've written. Which one looks like that equation that we have there? From all the equations we've written, that particular one that we have there, which one looks like it?
Question 2.
Equation 2, awesome. So I'm going to be copying equation 2 now. I'm going to be copying this same equation 2, all right, into our question. Oh, awesome. So to illustrate that, this looks like this. Now they said calculate the amplitude, find the amplitude. What's the amplitude? What looks like the amplitude there?
0.02.
Sorry?
0.02.
Okay, so the amplitude is 0.02. The amplitude there, as you see there, is just 0.03 meters. 0.03 meters. Okay, that's just a quick way to answer that. The next thing they asked us to find is to find the what? What did they ask us to find there?
The wavelength.
Wavelength, awesome. Now, for us to get the wavelength,
Do you see this
remember, in solving wavelengths,
DSTV?
from K, let's go back to that question. Okay. This question is also rearranged as this K. If you check here, 2.2 here is K. Okay, it's actually 2.2. Okay, it's 2.2. Now let's go back to this. Let's come back to this. What is the formula for K? I wrote that somewhere here. K is actually what? From this place. K is 2 pi lambda, isn't it?
Yes.
From here, K 2 pi lambda. Awesome. So I'm going to be taking it up from here. And I'm going to come here. K is actually 2 pi lambda. Imagine, we know K and we are asked to find lambda. We know K, we have 2 pi. I hope you know why how I got K to be 2.2. I hope you know why.
Yes.
Okay, so now K is equals to 2 pi lambda. So tell me, what would be lambda? God, I have made this.
2 pi over 2.2.
I've made almost the same mistake I did before. Come on, that's wrong. Sorry, what did you say?
2 pi over 2.2.
Come in. I think I made, okay, lambda is equals to what? 2 pi. Okay, that's 3
Over 2.2.
times 3.142 over what? Over what?
2.2. 2.2.
2.2. Okay, and that will be giving us what? So what's the lambda now? So what's the answer? They asked us to find, now, yeah, the next, okay, we said that's 2.87. The next thing they asked us to find is the big T, that's the period T. But remember that remember, we have, what do we call it? We know definitely that angular velocity is 2 pi f, which is also the same thing as 2 pi over t. Now, if we cross multiply, t is equals to 2 pi over w. I hope you remember that formula.
Yes.
Okay, we know definitely that, let me see if I could get the, oh, just import it, transfer it. Okay. Period T is equals to 2 by W, 2 pi over W. We know definitely that before now, angular velocity was equals to 2, is equal to 2 pi f. So, and f is 1 over big T. F is 1 over big T. So, which when we cross multiply, big T is equals to 2 pi over angular velocity. Now, from that question, what is the angular velocity there? From that question. From the question there, what's the angular velocity? That's comparing the equation 2 with that question, with that equation that was given to us. What's the angular velocity there?
3.5.
Correct. 3.5. Now, the angular velocity there was given to us as 3.5. That's, the angular frequency there, which is 3.5 radian per second. Now, I want you to slot in angular frequency. That's 2 times 3.142 divided by 3.5. That gives us the period. So tell us what's the period from there. He said it is 1.795, 1.7, okay, 95. Okay, let's approximate it to 1.80 seconds. Okay, 1.80 seconds. Okay, now, what did they ask us to find next? They said find the speed of the wave. What's the formula for speed? What's the formula for linear speed? I guess I've given you that formula before. Sorry?
Angular speed times radius or amplitude.
Times what?
Radius or amplitude.
Okay, now, sorry. Now we have, look at this. You said angular speed is equal to a radius times what?
Amplitude. Angular.
Um, go back. Go back to the formula for when we talked about, okay, let's go back. Let's check. V, I gave you the wave velocity is equals to distance over time, isn't it? And I said the V is equals to the wave length over the period. Then V is now equal to frequency times lambda. Did you remember that? I guess we solved the question on that.
Yes.
Yes, the last time we met. Okay. Now with that now, we have with that now, that becomes very easy for us to solve this question, because you might be surprised that, oh, we don't have, even if this was not given, you may be surprised that, but sir, we don't have the frequency. You know how to get frequency when you have your big T already. You know that frequency is actually one over big T, one over the period. So with that, with that alone, you can actually get your frequency and then multiply by your lambda. But if you don't want to go too far, you could just say lambda over big T is the same thing. It's the same thing as frequency is equals to 1 divided by big T. So V is equals to lambda over T. I hope you understand that.
Yes.
Okay, so you fixing your lambda there over big T, and tell me what's the speed.
1.59.
Okay. What's the unit, please?
Meters per second.
Okay, meter per second. So this is how to solve simple equations involving wave. All right, I'll give you one to try on your own now. This was like an example, even though you did much of the work yourself. Mm, okay. Okay. Um, okay, take this question. A plane progressive wave, a plane progressive wave um, okay, let me write it down. A plane progressive wave, oh, sorry, wave is represented by the equation. Now, this is a question. A plane progressive wave is represented by the equation 2 sine into brackets 2000 pi t minus 0.5x, where the symbols have their usual meanings. What is the frequency of the wave? All right, I'm going to give you some minutes to try out this by yourself. So you can decide to try this out by yourself and tell me the frequency of the wave. Do you understand that?
Yeah.
1000 hertz. Wow, awesome, awesome. How did you go about this? Wow, awesome, awesome. Now this is awesome. This is awesome. Okay. Um, I love this progress. This progress is wonderful. Now, let's continue. Let's see another question on this. Let's see another question on this. This is awesome. Okay. Now look at this. Okay. The equation of a wave is given as, please write this, and you solve this also. Equation of a wave is given as y is equals to 0.5 sine 3 pi x plus 50 pi t, where x and y in meters and t is in seconds. Find the amplitude, the wave number k, and the wavelength of the wave. I'm going to be adding the frequency e, the time, f, angular speed. Okay. These are things I believe you should be able to do. Okay, so I'll give you some minutes to work on that also. Wow, this is awesome, but most of your values don't have units. Most of your values don't have units. An example is your amplitude, your time, your period, and your angular speed does not have units. Okay. Now you might need to remove that pi to make it 50 times 3.142. So you can have, because if it's in pi, it's most likely meant going to be in radian. So I would appreciate you make it 50 times 3.142 so you can have your answers in meters per second squared. Are you done with it now? Okay. Okay, I'm going to give you the last question that you should solve. It's a very wonderful question before we call it a day. Okay, awesome. That's meters per second, right?
Yes.
Okay, I'm going to give you one last question to solve before we call it a day, and that's this. Okay, go through this question and try see how you can solve it now. Now, the second one says, but you know the wave velocity, right?
Yes.
What's the wave velocity?
60.241.
60?
0.241.
The wave velocity that's the same V now, so it's frequency times lambda, isn't it?
Yeah.
So that would just be 12. You have your frequency as 12, you have your lambda as 5, so it's just 60 meters per second. All right. The crest, they said if the crest at x is equals to 3 meters at time feet, find the 3 other position of the crest at that instant. Remember, what do we understand by crest? Now, crest, I did mention to you a definition of crest. which was, can you remind me what is crest? What is crest? That's the region of maximum upward displacement of the particles of the medium. So for that question, if there is a crest at x equals to 3 meters at time t, the position of the crest at that instant would be 3 plus the wavelength. So the first position will be 3 plus 5, which is 8. That will be 3 plus 5. The next one will be 3 plus 5 plus 5. Remember, the wavelength is actually the distance between two successful crests. So that the next distance will be 3 plus 5 plus 5, which will be 8 plus 5, 13. And the next one will be 3 plus 5 plus 5 plus 5, which will be 18. So that would just be the crest. Now the next one said, what time later? The next one said, what time later will there be another crest at x equals to 3 meters? Now it says, what time later will there be another crest at x equals to 3 meters? So the at x equals to 3 meters, that would be after one period. So the time would be, remember we have a frequency, so they're just asking us to find the time. What time a crest will arrive again at x equals to 3 meters after one period, t. So that means the t will be 1 over f, which is 1 over frequency, which is 1 over 12. The frequency is 12. And the next thing they ask us to find is, if the amplitude of the wave is 1.5 meters, write the equation of the wave. If the amplitude of the wave, now we are going to write the wave equation based on what we have, based on the values we're given. Okay, and from the values we're given, we have from the values we're given, a sine, that means we'll be using 2 pi. We have the lambda to be 50. Sorry, we have lambda to be 5, not 50, sorry. We have the velocity to be 60 t, and we have we could also have our x. So from this now, the equation, what is amplitude?
One point five.
You said
1.5 meters.
okay, amplitude is 1.5. That will be 1.5 sine 2 pi over lambda. Lambda is 5 in brackets. We could just use Vt minus x. Vt minus x. And what is V? V is 60. That will be 60t minus x. So that can be our equation. Our equation will be 1.5 sine 2 pi over lambda. That's 2 pi over 5 in bracket 60t minus x. Do you understand that?
Yes.
Okay. So we can have the equation as, let me write it out. We can have the equation as this. Or we can have the other one as this. Okay. We can still have it like this. It's the same thing. Any of them you choose is the same thing. Okay. Let me give you something to work on. Probably that you could use to maybe you could like an assignment. Okay. The assignment would be given in this form. So you could just snap it. Wow. Oh, that's quite lengthy. Okay, you could snap it. Okay, just take a photograph of this and let me know if you've done that. This is number 1. Number 2. Number 3. Have you taken this? Have you snapped it? Oh, this is number 2. Okay, have you snapped it, please?
No.
Sorry? You can
No.
screenshot it now. I mean, snap. You can snipe it. Okay, I guess you've done that now.
Yes.
All right. There are even 5 questions. This is the 5th one. Okay. If you've done that, you could just send it to me and I will look at it. All right, let's pray. Father, we thank you for today. Thank you for how far you've helped us. Blessed be your name forevermore. In Jesus' name I pray.
Amen.
Pray for wisdom and greater understanding upon your daughter and everyone in the name of Jesus.
Amen.
In Jesus' name I pray.
Amen.
All right. Have a wonderful time. Yeah.